So yesterday I reviewed a little bit n equals 2 four-dimensional supersymmetric gauge theories, and some of the ways they can be embedded in string theory or in M theory, that is to say, viewed as low energy limits of string theory compactifications. And today I will start by completing this overview by giving two more ways of embedding n equals 2 gauge theory in string theory. So one option is to, so yesterday what we did, we started with the maximally supersymmetric situation where you had, let's say, ND3 branes, which normally gives rise to the maximally supersymmetric Young-Mills theory n equals 4. And then well, modify transverse geometry. So replace R6, which is the transverse space, by an orbifold where gamma was a discrete subgroup of SU2. So that gave a class of superconformal n equals 2 theories in 4 dimensions. So today I want to describe something else, also starting with the maximally supersymmetric situation, but then doing modifications both in transverse space and in longitudinal space. So start with ND5 branes wrapped on a two torus. So this is still in type 2B string theory. So macroscopically, this is the same starting point as before, because microscopically you have a 4-dimensional world volume. So they wrap. But now let me modify this theory by adding a twist of the normal bundle over T2. So you see here the transverse space is R4. And so if the geometry is just flat R4 cross T2, we have the maximal supersymmetry as before. But now, if I replace the direct product by a twisted product. So this is, well, it's a quotient of flat Euclidean space R6 by the action of the lattice, which acts simultaneously by translation in R2 and rotation in R4. So I'm trying to construct a geometry which is locally flat, but globally it's non-trivial. So as you go around these cycles in the two torus, your 4-dimensional space experience rotations. And so there are two basic rotations. You can have the rotation corresponding to the A cycle and the B cycle on the torus. So these are the elements, two elements of the group SO4. And for, first of all, in order for this thing to glue together into a nice smooth geometry, they have to commute, because on the torus you can continuously deform, going along the A cycle and the B cycle, or the other way around. So they have to commute in SO4. And then the other condition is that we still want to preserve some supersymmetry, because well, we want to construct a supersymmetric gauge theory after all. So if you keep these rotation parameters generic, then you would break all over supersymmetry, because the spinors which generate supersymmetry transformations get rotated. Unless these rotation matrices preserve some spinors, you will lose all covariantly constant spinors. So we need to preserve some spinors, and well, if you look at them as sitting inside the spin group, which is the product of two SU2s, the condition that they have at least one spinor which is preserved is that these rotation matrices actually belong to one of the SU2 subgroups. And so, so let me pick one. And so now, from now on, I'm assuming that GA and GB belong to the SU2, to some SU2 subgroup. Now, they're still commuting. So they can be simultaneously diagonalized. And so there are actually two real parameters in this twisting procedure. Which are the eigenvalues of these two matrices, and eventually, well, something like the complex linear combination mu A plus I mu B divided by something like the radius or the square root of the area of this torus becomes a mass parameter. So this is a complex mass. So the resulting theory, in the limit when the torus becomes really small, so we take the limit when r goes to 0, mu go to 0 in such a way that m is constant, m is fixed. The result is the so-called n equals to 2 star theory, which is un n equals 2 plus adjoint hypermultiplet of mass m. So what's the physics of that? Well, you see, when you look at the scalars which live in the gauge theory on this stack of branes, these scalars, as far as supersymmetry is concerned, belong to either the vector multiplet or the hypermultiplet. And this geometry is such that, well, there is a clear distinction. The space which is transfers to the physical Minkowski space, so it has, which is 6-dimensional as before, here splits into 4 plus 2. 2 is within the torus, and 4 is the vector space. So this 2 will belong to the vector multiplet, and this 4 will belong to the hypermultiplet. Now, the scalars describe the fluctuations of the brane, the way you move things around. So if there is no twist, if this is a direct product, it costs you no energy to move your branes along this 4-dimensional space. But if it is twisted, if you try to displace your stack of branes from the origin about which you rotate things, as you come back, you will not come back to the same point. So some things will get stretched at some point. And so it will cost you an energy which is equivalent to an energy of a particle of mass m to move things. And so that's how you can qualitatively understand that some of the degrees of freedom which were massless in the maximally supersymmetric situation, like here, will become massive here. Or you can also just do the direct analysis in Lagrangian, just by doing, if you like, the Kaluzic line reduction on the space with the metric of the form So this is the metric on the 2 torus, which I'm taking for simplicity to be just a square torus with 2 sides of size r. And then for the for this R4 piece, I'm taking the metric to gauge field. And this whole thing is such that it's actually, in Dirac monopole, gauge field cannot be written globally. It has a singularity along a string, which is the gauge artifact. But it actually has a singularity at the center of the monopole. But this is where this function v has a pole, and so v inverse has a 0. So this whole thing actually is non-singular. It's a famous metric. A counterexample to one of Einstein's statements, I think. No? Anyway, what's special about this space is that this is a hyperkähler manifold, and as such, it has covariantly constant spinors. On the other hand, if you look at it at this space near r equals to 0, this is nothing but R4. This is just R4 written in some strange coordinates. So if you take R4 and parameterize it, let's say, by 2 complex numbers, then this vector R is just z1 squared minus z2 squared, real part of z1, z2, imaginary part of z1, z2. So just take the flat metric dz1 bar plus dz2 bar, and we write it in terms of this vector, and the remaining phase, you will get that. So in the limit when r goes to infinity. So when I say that you cannot replace R4 by this Taub-Nut space, it means that you change it asymptotically at infinity. You replace the you modify the geometry at infinity in such a way that you actually get a circle of finite size. But near the origin, you don't modify anything. And when you do these manipulations with a twist, you're only interested in the local geometry near the origin. So this is just as good. On the other hand, this space is interesting. It's nice because it has this special U1 isometry. Which is just shifts of this coordinate theta. And you can do T-duality with respect to this isometry. And also, because we have this 2 torus, and we're interested in the limit when the torus is small, it makes sense to T-dualize, so just to make it large. And the fact that these 5 branes were wrapping these 2 torus, in the T-dual picture, they will be localized, and the transfer space will be almost infinite, which is a simplification. So we do 3 T-duality. 3 T-dualities. So 1 along the tau knot theta direction, and 2 along the 2 torus. And what will you get? Well, okay, the d5 brane. So first of all, you will map type 2A to type 2B to type 2A because you made an odd number of T-dualities. Every T-duality changes the A type to B type and vice versa. Now, the 5 branes were wrapping the 2 torus. So when you T-dualize along the 2 torus, you lose dimensions. So after 2 T-dualities, these d5 branes will become d3 branes. But then you're T-dualizing in the direction which is transverse to this brane. So you will gain dimension. So eventually, these 5 branes will become a stack of d4 branes. Now, this tau knot, so this R4, which became tau knot, well, the way it's written, the T-duality will naively just invert the radius of this circle, this varying circle. So if in the tau knot metric, the coefficients in front of the dr squared and d theta squared are inverses to each other, but after T-duality, V inverse will become the inverse of that is phi. And so it will be just a conformally, the metric will become conformally flat. In fact, conformally, the metric on S1 cross R3. But then there is also a dilaton shift. And so when you map to the string frame, eventually you will actually get a flat metric on okay, so let's first get to tau knot. So tau knot naively will become S1 cross R3. But because of this non-trivial part of the metric, which is like the Kaluza-Klein gauge field, after T-duality, it will become a B field. And so, so the B field with non-trivial flux. And so, if I draw this circle, it turns out that what you get a single NS5 brane, which is localized somewhere on this dual circle. So this S1 is dual to that circle theta. So let me call it theta. Check. And then, so these 5 branes after T-duality will become a stack of D4 branes and D4 branes, which actually end on this NS5 brane while wrapping this circle, S1 theta check. And they actually break apart on the NS5 brane, and there is a distance m, which is the parameter m which I had before, along the NS5 brane. So to make this geometry a little bit more clear, the directions within an S5 brane, which are not parallel to the directions within D4 brane, are actually 2-dimensional. And so the separation between the two endpoints of the default brane is can be described by a single complex number, which is this number m, which is the mass. And so this massive hypermultiplet, which I was talking about, is just an open string which starts and ends on the default brane and tries to minimize its energy by occupying the shortest, by stretching along the shortest path connecting two endpoints of default brane. Yes?
What determines the winding number of the defaults along the S1?
So it's the fact that so in the original geometry, these D branes were not wound around the S1, and we titularized once. So the usual story is that when you titularize along the circle which is transverse to the D branes, after titulation, you'll get D branes which will be wrapping the dual circle once. So the winding number is essentially related to the number of branes. So you could trade number of branes for the winding number.
Yes,
and
the
shift is a different story. The fact that there is a shift, it's a different story. So that's you. So this shift is the consequence of the fact that this Taub-Nut space was not a direct product of the torus, but it was this twist in the story. So. So when you do this duality carefully, it's after you include these factors, you will get this shape. Now you can actually, okay. You can draw this geometry in a somewhat different fashion. Namely, you can think of the so I'm trying to draw the following situation, that I have a circle, and now I have an R2 bundle over the circle, such that as I go around the circle, I experience a shift in the fiber in the amount of m. So it's again one of these cross products, if you like, except that this is not a vector bundle, but it's a affine bundle. I should probably draw it on that part. So it's easier to understand the geometry if you go on the covering space. So let it be the universal cover of the S1 theta check. And then these are the preimages of my NS5 brane. So in the direct product situation, you would be identifying a point here with a point here. So that's the usual story. This is the m equals to 0 case. But when the m is not 0, you identify the point here with the shifted point in this image, and so on. So you start with with default branes, which if they do not break will be stretching across this line, which has some angle, but it is energetically favorable for the default branes to break, and because they're so heavy. So they still stretch in this way, but the open strings which connect one piece of the default brane with its image pays a price. So it has to. So it cannot be shorter than m. So this is an example when one small member of a community sacrificed himself for the greater good. So the branes are heavy And so the volume is much more important than the length of an open string, which is much lighter. OK. By taking an appropriate limit, actually, if you now take a limit when m goes to infinity, and the gauge coupling goes to 0. So I didn't explain what was the gauge coupling in this story. Well, OK, let me skip that. So there is a limit when So you can take a scaling limit when you send the mass of the hypermultiplier to infinity, the gauge coupling to 0, the gauge coupling at some ultraviolet scale, in such a way that this quantity, which is essentially the contribution of an instanton, remains fixed. And that's so the gauge coupling is related to the size of the this bare gauge coupling is related to the radius of that circle. And so there are several factors which go into this. So so there is a way of redrawing this picture in which you would see effectively two images will actually go closer together, and you will not see the periodicity of the circle. Okay, so let me just draw the end result of these manipulations. You actually see two NS5 branes and just n d4 branes which are stretched between them. And this distance will be of the order of logarithm lambda. So this is the limit. It's an elementary. It's a planimetry. So the previous lectures were reducing everything to the elementary school arithmetics. So this is the elementary school planimetry, and I will leave it as a homework. So derived from that periodic picture with a shift, this picture with no periodicity, and but there are two NS5 branes, between which there are n d4 branes. And so this is the setup which Witten suggested at some point as the simplest realization of the pure n equals 2 SUN superioung theory. So if you think about it in field theoretic terms, so the previous construction started with the classically six-dimensional Young superioung theory, and then imposed and then compactified on the two torus with twisted boundary conditions, such that in the limit when the torus was small, you got four-dimensional theory with the mass term for the hypermultiplets. This construction starts with the maximally supersymmetric Young-Mills theory in 5 dimensions, but then subjects it to the boundary conditions in strict sense, so that you put the 5-dimensional theory on an interval and impose appropriate boundary conditions at the endpoints of the interval to reduce supersymmetry. So, and so one is limit of the other, actually. All right. Now, yes?
I just didn't understand how you got the NS5 brane originally. My question is,
Okay, so just something to keep in mind. So the T-duality of Taubnat along the U1 theta isometry gives you the NS5 brane with transverse circle. So if the Taubnat had this radius r, which was this asymptotics of the, let me call it r infinity, of this v function, then I suppose that circle will have the radius, well, it's actually r squared, if dimensions are right.
So if you consider multi-center tau naught, then you will get a quiver?
If you take a multi-center tau naught, which means that here you have, well, we'll have, let's say, m poles, then you'll get m NS fibranes, which will be, I mean, depending on the separation, will be separated in some directions. And if you, in addition, you had D4 branes, then you might get, well, you may, so there are several options. So you may get the gauge series of corresponding to these arrangements of D4 branes, and which are indeed described by quivers. And so if there is a circle, I mean, if we're within this framework, there is a circle, and so this will correspond to the AM quiver we had last time. So this is the. So this is precisely the theory which I discussed last time. So we have, there are m plus 1 nodes, and so if the number of branes here are all equal, which from the brain dynamics point of view, this is just the zero force condition, that they pull the NS fibranes, which are in between, with equal force in all directions. So then you'll get superconformal theory where you have m plus 1 UN gauge group factors, and there are bifundamental hypermultiplets, which are the open strings which are stretched between the neighboring stacks. Okay, so these are the. So this is this brain gymnastics, which at first is just one way of visualizing the various theories you can construct, but in some cases it actually helps you to solve these theories in the sense of understanding the low energy dynamics without much work, which is a bit deceptive because you actually need to be able to identify what you see in these pictures with actual gauge theory observables. And that's sometimes it's a non-trivial job. But one instance of this construction is the famous approach of Witten, where you lift this picture now to M theory. By lifting means that just try to understand what this picture means in M theory. And whereas in type 2A, it looks like you have a construction which is built out of different ingredients. Here are D4 branes which support gauge dynamics. Here are NS5 branes which support something trickier like non-abelian tensor dynamics. When you lift them to M theory, they all become different parts of the same object. So you get a single you get single M5 brane, whose geometry is such that when you so there is a circle which you add when you go from M theory to string theory. We call it S111. So these D4 branes, which are 4+1 dimensional, actually become 5+1 dimensional, and there is some thickness which we add to this picture, which is of the order of the radius of the circle. And they're glued smoothly to these NS5 branes, which become just the asymptotic components of the single curve. So it becomes a complex curve. And the fact that it's complex, it's a consequence of the desire of the M5 brane to minimize its volume. So complex surfaces, complex curves, holomorphic curves minimize the area in a given with given topological restrictions. So that's a way to see what is called the Seiberg-Witten curve, just without much calculation. So you just need to find an appropriate family of curves to match all the parameters which you have on the gauge theory side. It doesn't tell you much, actually, how you get to this curve from the gauge theory point of view. You just say it, well, that from what we know about M theory, this is what it should be. But of course, since we don't have a fundamental definition of M theory, this is not a very convincing derivation. So what I want to start talking about now is how we compute, how we derive these curves for all these theories, starting with gauge theory. So just doing the quantum field theory computation. Okay. So what are the effects, actually, which are responsible for, let's say, here? What are the things which, in type 2A string, which reveal the existence of the 11th dimension? So how do we know that there is an 11th dimension? So, for dark matter and dark energy, you go to W map, but for the 11th dimension, how can you check that it exists? Well, you study supersymmetric quantum mechanics, and the supersymmetric quantum mechanics of D0 branes. So one way to guess that there is an additional dimension is to see a tower of Kaluzic line particles. Well, so there are Kaluzic line modes of the graviton, of the supergraviton, which are D0 branes and they bound states. And so anti-branes as well. So the bound state of M the bound state of M D0 branes is the mth, M is a Brent number of K. It's kth Fourier mode. Okay, so somehow if we include the effects of these D0 branes in this picture, we should be able to, after resumming it somehow, we should be able to visualize that there is a circle which will change the one-dimensional geometry of these D4 branes into the two-dimensional geometry of this Riemann surface. So somehow we need to take into account the effects of D0 branes. But these should not be the effects of D0 branes which could in principle propagate everywhere in the bulk. We only need to care about the D0 branes which somehow are bound to the D4 branes, because this is what we want to thicken. So what happens is that these D0 branes can actually attach themselves to the D4 branes, and in particular, one thing which you can do, they can actually travel from one NS5 brane to another in finite time. And so you want to take into account these trajectories of the D0 branes, if you like, the Euclidean trajectories, which in 4 dimensions, in the physical 4 dimensions where the gauge theory is living, will be localized both in space and time. So D0 branes bound to D4 branes and propagating from one NS5 to another. So these are events in space-time physics which happen at fixed space and fixed time. So these are instantons. So we learned that if we take into account, well, we suspect that by taking into account the instanton effects in gauge theory, we would be able to lift this picture to the higher dimensional picture. And so, so this is what we should do, gauge theory. Now, what do I mean by taking into account the instanton effects? Well, let me start with the simplest example of taking into account first of all, let me remind you what is the instanton. So in four-dimensional gauge theory, in Euclidean space-time, the Yang-Mills action is, well, it's E squared plus B squared is positive definite. And in fact, it is bounded below by the topological quantity, which is the instanton charge. And which is, depending on normalization, is in some units, it's just an integer. And so this bound is saturated by the solution of the self-duality or anti-self-duality equation, depending on the sign. And my convention is such that for k positive, I will take the minus sign here. So this is something which is called the anti-self-dual gauge field. So the solutions to this equation, they are localized in space and time, have some typical, well, for k equals to 1, the solutions have some, the energy, the action density has some profile. So these instantons, they are localized somewhere near some point in space-time, and they have some typical size. And so the location and the size are the examples of the so-called instanton moduli. Now, in 5 dimensions, in 4+1, in the theory on D4 branes, which is a 4+1 dimensional theory, the solution to this equation will describe a configuration of finite energy. So so there it will describe not, so it will actually describe a particle, a solitonic particle, and according to the general story, in quantum field theory, when you discuss the spectrum of particles in this theory, in addition to what you get just by expanding the Lagrangian about a minimum potential, which leads to the ordinary quanta, you also have to quantize the moduli of the solitonic solutions. And whatever normalizable wave functions you will get the additional particles in the spectrum. And so we need to perform this analysis of this moduli of instantons to understand what kind of bound states of clumps of these D0 branes with a stack of n D4 branes we might have. So what kind of particles we will get. So we have a modular space of k instantons in UN gauge theory. And upon quantizing, we'll get the spectrum of solitons. And these solitons, they are typically charged under the gauge group. So when you compute the loops, which these charged particles, the loop effects, they will contribute to the running, for example, to the running of the effective gauge coupling. And so that's one way to understand the instanton corrections to the effective action in 4 dimensions. So the loops, or here they're actually not quite loops, these are propagators between one NS5 brane to another NS5 branes. Of these solitons produce the running of effective gauge coupling, and they produce the corrections to the effective action. Now, so in order to discuss these corrections in some efficient way, I need to say a few words about what kind of structure this effective action has. And this is where the n equals 2 supersymmetry becomes important. So what do we expect in general? We start with SUN gauge theory. And if you just look at the classical Lagrangian, so remember there was this scalar in the vector multiplet. So this is the SUN vector multiplet. There's a term in Lagrangian which is the commutator, trace commutator of this complex scalar with its conjugate. So it is minimized classically when phi commutes with its conjugate. And so it means that you can diagonalize it by gauge transformation. So A's are complex numbers. So if you're sitting in a classical vacuum where phi has this expectation value, where the eigenvalues are distinct, then what you see n abelian U1 vector multiplets. So these are the vector multiplets whose lowest component, whose scalar component is the corresponding eigenvalue. And then, well, when you just expand, the off-diagonal components of phi have masses so these are the vector multiplets where W bosons belong. They also have masses of the order, the difference of these eigenvalues. You can see that for the scalar component of the vector of a W multiplet, you can just see it from this potential. And for the vector components, you have to look at the scalar kinetic term. So what you expect that the low energy effective action would be that of the sigma model on the space of these eigenvalues A. So the coupled to the abelian gauge theory, with some matrix of effective couplings plus some fermionic terms, and plus you actually could induce a matrix of theta angles, which also depends on the scalars. So if you're interested in the effective action, which is only two derivatives in bosons and limited number of fermions, 4 fermions in fact, then essentially what you need to compute are these three matrices: the matrix of effective metric on the space of A's, the effective couplings, and the effective theta angles. Now the supersymmetry tells us that, first of all, this is actually the correct target space, that what looks like a valley of classical vacua remains a valley in quantum theory. And then the supersymmetry also tells us that actually there are relations between these three matrices, and in fact they all are derived from the same, from a single function. So there is a function of which is a holomorphic perhaps multi-valued of its eigenvalues A, such that the effective metric is just the imaginary part of the matrix of second derivatives. And now out of H and theta, we combine, well, if we take this linear combination, this will be just the matrix of second derivatives. In other words, we can rewrite this term, what we call tau. We can rewrite this as tau ij times the anti-self dual part of the ith field strength and tau bar multiplies the self dual parts of the field strengths. So in n equals 1 supersymmetry, you know that there is a relation. So the metric which you find in front, which the metric on the target space would be from the n equals 1 supersymmetry, it would be just scalar. So you would expect that it is the second derivatives of some real function with respect to A and then A bar. And then n equals 2 supersymmetry tells us that this function K, so this is n equals 1, and n equals 2 says that K is more special than you could suspect. That it has something like, it has a structure which is of that type. So we need to compute this function f. This function is called prepotential. And the first computation which you can do, you can just do the perturbative computation. So just, as I said, expand the Lagrangian in, around this vacuum. So you will see the quanta which you see will be those of W bosons as massive fields. So the first thing which you can do, you can compute the one loop contribution of W bosons to the beta function. Now, so when you compute the, so this is the, let's say, so these are these U1 photons, AI, AJ, and this is the W boson, which is IJ component. So since it's a massive field, depending on the, so if the external momenta Q is very large, well, if it's much larger than the mass of the particle which is in the loop, well, you get the usual logarithmic running of the effective coupling with the momentum. But now, if my momentum becomes much smaller than, well, as soon as it becomes smaller than the mass of the W boson, the running stops. So the point is that when you're sitting at different points in this modular space of vacua, so in the ultraviolet we'll all start with the same coupling, and then we start running the RG flow. When it stops running, when the effective coupling stops running, it depends on the mass of a W boson for a given point in the modular space of vacua. So for a point A, the running stops at Q squared equals absolute value of AI minus AJ squared for a corresponding coupling tau IJ. So if we normalize the coupling is such that so that at the ultraviolet the coupling is universal, then what we'll get in the infrared will depend logarithmically on that mass. And so so what this leads to is that at one loop, tau ij is the logarithm of AI minus AJ, well, divided by some normalization scale, lambda, with some coefficient here, some numerical coefficient which I don't want to write down, and that's it. So that's all there is at level of one loop computation. So when you compare it to the textbooks where usually the running of the gauge coupling is given as a function of the momenta, it's a logarithm of the ratio of the momenta squared to the mass of the intermediate particle. And here we see the mass of the intermediate particle divided by the ultraviolet's cutoff, in a sense. So this lambda is the ultraviolet. So you can write it as a classical tau ij plus the ultraviolet cutoff here. And you absorb so when you normalize, you send the cutoff to infinity, you scale the classical coupling in such a way that the combination, which I wrote on the blackboard before, remains finite. Okay, so this is what you get at the perturbative level, and then the non-normalization theorems say that you don't get anything else at the perturbative level, and then you know that there have to be there ought to be other corrections because this logarithm, well, it's a complex valued function, but when you look at the effective metric, which is the imaginary part of that, and I think there is an I here over maybe 8 pi squared. So perturbatively, this will be something like log of absolute value AI minus AJ over lambda. So when the distance between the eigenvalues becomes smaller than lambda, this changes sign. And so the effective metric becomes negative definite, so the theory loses unitarity. So something has to cure it. And what happens is that actually, in addition to this one loop, there are instanton corrections, which will go as power, which will be power-like corrections which will be such that when you try to make the eigenvalues too close to each other, these corrections become important. So the yes.
Is there a simple way to see that there is no higher perturbative correction?
I don't know what is the simplest way. So, so one approach is to use this. You can actually, well, if you can, okay. So one way to do this is to do the background field computation in the background of an instanton, where in this effective action, let's say if f plus is equal to 0, so you will still have f minus, and then you can detect what the coefficient in front of f minus square term is to read off the effective coupling. Now, if you are sitting at the background where f plus equals to 0, then this background preserves supersymmetry. So there is some supercharge which is preserved by this background gauge field. Now you can organize your Feynman graphs into a kind of a supergraphs where you will be integrating not only over the momenta, but also over the odd variables which will be translated by that particular supercharge. And the fact that it's a symmetry would imply that if the diagram is convergent, which is what you expect for high loops, then because it's a symmetry, there is fermionic integration which can be taken out of the Feynman diagram. So there is the integrand, the propagators will not depend on this fermionic variable, which is translated by this supercharge. And so the result will be 0. So in short, if you had the super Feynman graph techniques for this theory, then you would just say that there is one additional fermionic integral which you cannot absorb, and so it gives 0. But there are other ways of using this fact that there is a background which preserves supersymmetry, which are more universal, I would say. Okay. So, okay, so the point is, now the point is that this prepotential function. So I wrote what tau is at one loop. It was a logarithm, but I claim that tau is actually second derivative of a single function, and it's not obvious that the logarithm of ai minus aj can be written as such a derivative, but in fact it can. So there is this remarkable function So this is one loop. So this is the one loop contribution to the prepotential. This is called the prepotential. So in bosonic theories, you have potential. In n=1 supersymmetric theories, the potential is computed from the superpotential, and in n=2 theories, there is a prepotential from which you derive everything. So by dimensional counting, you can argue that so I'm talking about the pure SUN n equals 2 theory here, but we could make this discussion more general. Where Rn is homogeneous rational function of degree 2 minus 2nn. So this guy, the one loop term is almost homogeneous of degree 2 up to this logarithmic anomaly, and the remaining guys are precisely homogeneous of degree 2 if you assign a scale 1 to lambda. So these Rn's are given by the integrals over the moduli spaces of instantons of charge n with gauge group SUN of some measure, which depends on A. And so it's the goal is to determine what this measure is, what these integrals are, and what this whole thing is. Now, in 1994, Zyberg and Witten explored this problem without trying to calculate these corrections directly, just based on a few constraints which you can impose on the structure of this function f, just following from the holomorphy, which is the supersymmetry constraint, and an additional constraint, which is the fact that since the effective theory is the theory of abelian multiplets, abelian gauge theory has the electric magnetic duality, which which replaces electric fields by magnetic fields. On shell, it replaces the curvature, the field strength of the gauge field by the dual of the field strength of the dual field. What's a bit trickier is to perform this duality at the level of the quantum theory. And what's even trickier is to understand that this actually persists when you couple the abelian gauge fields to the sigma model, which we discussed. And it turns out that the structure is such that this whole thing is actually covariant under this electromagnetic duality. And under this covariance, the variable A, which was naively parameterizing the eigenvalues of the Higgs field in night-joint representation, could get mixed up with the derivative of the prepotential with respect to A. So the significance of this quantity, the derivative of f with respect to A, which is called A dual sometimes, is that whereas A defines the masses of W bosons, so particles which you see in the perturbative spectrum, A dual determines the masses of monopoles. And since you have many U1 factors, you have different types of monopoles. So I'll just write. So this duality is not actually symmetry of the theory, because W bosons are very much different from monopoles in n equals 2 theory. And as well known, it's a symmetry of n equals 4 theory, where they all belong to the same multiplets. But nevertheless, the point is that as you go around, as you wander around in this vacuum space, you actually the appropriate parameterization of the vacua and of the theory may involve different variables at different corners of the moduli space. And so, whereas naively you would say that the good degrees of freedom in the theory which we started with were photons and W bosons, when you go to a strong conflict regime, you might actually lose W bosons. They actually may cease to be stable particles, and you also will be left with monopoles which are much lighter than W bosons. In fact, there is this interesting story about what do you call elementary particles. So the monopoles are much heavier. So naively they could be much more localized than W bosons, and you could treat them as elementary constituents. Of course, as we know, even though the monopoles are heavy, they are not. The Compton wavelength has nothing to do with the actual size. So anyway, so there are interesting discussions about this. The point is that what you call the appropriate degrees of freedom at different corners of modular space are different, and so you need to find a description which will be adapted for these electromagnetic duality transformations. And so what Zyberg found was that you can actually obey all the constraints of holomorphy and electromagnetic duality by producing a family of curves and so this is one of these curves. So these are complex curves which depend on some parameters, U1, Un, which will be the global parameters, which could be identified with vacuum expectation values of some gauge invariant observables, like trace phi to the I, or could be some other parameterization. And the curves with differentials, so lambda is one differential on C, such that both A and A dual would be the periods of these differentials along the A cycles or the B cycles on this curve. So in this picture, so this would be the A cycles, A1, A2, A3, and so on. Or maybe the differences. I mean, there is of course, there is some freedom in the choice, what you call A and what you call B. And that freedom actually is the electromagnetic duality. And this would be the B cycles. Right. And so on. So, and so that the tau would be just the so-called period matrix. Of C. So that so the period matrix is something you define for any smooth curve, or for the curve with punctures with some conditions on the punctures. So there is a for a genus G curve. So the genus is a number of handles. So here is the genus 4. Suppose. So you find you can find precisely G holomorphic one differentials. They're defined up to taking linear combinations. So you can normalize them with respect to the A cycles, so that the periods with respect to A cycles are 1 and 0. And then after you normalize them, then the periods along the B cycles are uniquely fixed, and that gives you the period matrix. And what's so special about this matrix is actually its imaginary part is positive definite. And this is what we need for the effective action, because this imaginary part is the metric in the Siegel model. So this positive definiteness guarantees the unitarity of the theory. Although the unitarity of effective theory is another interesting topic which I'm not going to discuss, to what extent it's unitary. But at least it's not pathological. So the guess of Zyberg and Witten was to obey all the constraints by the appropriate family of curves, and then there was this whole. So they produced this family of curves for the SU2 theories with different matter content, and then several groups of people made intelligent guesses for this theory and for some other theories, but it's still nice. It would be. I mean, it was still desirable to get a direct derivation of both these curves and these corrections from the gauge theory, starting with non-abelian gauge theory. And so I will explain how this is done next time. Okay. I think I stopped. Yes?
Could you explain why you can't use the Berkeley type argument to relate the mass of the monopole to its size?
Why can I say, when I...
Well, you said that the mass of the monopole doesn't follow the usual Berkeley type.
No, the mass, so the mass of the monopole is the mass of W boson divided by the coupling squared, because it's a soliton. But its size, it's determined by its classical solution. So it's actually also determined by the mass of the W boson. The coupling doesn't enter there. You see, the Compton wavelength argument comes from the quantization. So you look at the wave, which describes the motion of the particle. And here the size is determined by the classical solution, which is...
But two canonical monopoles, the size is related to the mass, right? I mean, it's inversely, maybe I'm remembering.
But there is an important factor, which is gauge coupling, which is when it's small, it's a huge factor.
Is there any interesting structure for the higher
I'm sure there is. I'm sure there is, but I haven't explored it. I think, well, for higher derivatives, I think this question could be asked already for n equals 4, and I think there was some progress to that, but I'm not an expert. So the technique which I'm going to discuss will cover the prepotential and certain gravitational couplings, so couplings to supergravity fields. But as far as higher derivatives terms in the gauge theory, I'm not sure. In general, could you speak louder?
In general, if I want, I have if it goes to the
Yes.
this duality
Well, there is some limit to the number of dimensions you can go up here because I need this transverse tau knot, so you can't go. I'm afraid you cannot. You can go lower dimensions, but you can. Okay. I'm only scratching. I'm scratching the surface of something here. So there are many. So there are various subtleties and details which I was skipping and aspects of this which